let's look at a couple examples of using the second derivative test. So remember, the second derivative test says if you have a twice differentiable function and you have a critical point or a critical number for that function, then if the second derivative is positive at your critical point, then the critical point is a local minimum. If your second derivative is negative at your critical point or your critical number, then the critical number is a local maximum. And if the second derivative is 0 at your critical number, well, that doesn't tell you anything at all. You can't draw any conclusions from that. Okay, so for our first example, let's come back to a function that we looked at in an earlier video. So x squared over x squared plus 1. Sorry, f of x is x over x squared plus 1. In the previous video, we calculated the first and second derivatives of this function. This is what we got for the first derivative and for the second derivative. So let's find and classify critical points as local mins or local maxes, or neither, using the second derivative test. Notice that we could use the first derivative test, but if we already have the first and second derivatives, the second derivative test is actually faster. Okay, so first let's find critical points, or critical numbers. So let's take our first derivative and set it equal to 0. Okay, so setting this equal to 0 to find critical numbers. So first let's clear our denominator, right? The denominator is never 0, so we can just multiply both sides by x squared plus 1 squared. Our equation turns into 0 equals 1 minus x squared. So x squared is 1, and so x is plus or minus 1. So we have two critical numbers, plus 1 and minus 1. Now to decide if they're local mins or local maxes, then all we need to do is plug these critical numbers into the second derivative and see if what we get is positive or negative. So let's evaluate the second derivative at plus 1. We get minus 2 times 1 times 3 minus 1 squared, which is 1, over 1 plus 1 cubed. Now we don't really need to work out all of this arithmetic to know whether this is positive or negative, but if we do work it all out, let's see, it's going to be, negative 2 times positive 2, so negative 4 in the numerator, and in the denominator it looks like we get 8, so minus a half. And that's less than 0. So the second derivative at 1 is less than 0, so the critical number x equals 1 is a local maximum. It's easy to get this backwards and think, well, if it's less than 0, shouldn't it be a local minimum? But it's the second derivative that's less than 0. So that means that, right, we're at a critical number, so the slope of the tangent line is 0. And since the second derivative is less than 0, that means it's curving downwards, so it's like this. So that makes that a local maximum. All right, now let's check the second derivative at negative 1, the other critical number. So that gives us, let's see, minus 2 times negative 1 times 3 minus negative 1 squared is positive 1, all over negative 1 squared plus 1, that cubed. So let's see, in the numerator we're going to get 2 times another 2 is 4 over 8, so 1/2. And this is greater than 0, and so that means that x equals minus 1 is a local minimum. Now just to make sure that this actually is the case, let's graph this function. We have looked at the graph of this in a previous example, but we didn't really, I think we looked at the concavity of this function. We didn't really look at where the local mins and local maxes were. So this was f of x equals x over x squared plus 1, I think. Okay, so there's the graph. And if we look at the points 1, f of 1, and minus 1, f of minus 1, those should be our local mins and local maxes. And yes, those do look like our local mins and local maxes, and more importantly, the critical number at x equals 1, that is the local maximum, which is what we said it should be, and the critical number at x equals minus 1, that is a local minimum, which again is what we predicted using the second derivative test. So the second derivative test is working here. As long as the second derivative at your critical number isn't 0, you can use the second derivative test to distinguish local mins and local maxes. All right, let's look at one more example. Let's find and classify the critical points of this function, g of x equals x to the fourth minus e to the x. Of course, we're going to need the first and second derivatives of g, so let's calculate the first derivative. We need to use the product rule, so 4x cubed times e to the x plus x to the fourth times the derivative of e to the x, which is e to the x. Now let's calculate, actually before we calculate a second derivative, why don't we factor out that e to the x? So 4x cubed plus x to the fourth times e to the x. Now we can use this to calculate a second derivative. So we have to use the product rule to do that. So derivative of the first piece is 12x squared plus 4x cubed times e to the x plus the first piece with no derivatives, so 4x cubed plus x to the fourth times the derivative of the second piece, e to the x, and that's e to the x. To simplify this, why don't we factor out the e to the x, so we get 12x squared plus 4x cubed plus another 4x cubed from down here plus x to the fourth all times e to the x. So this second derivative comes out to be, why don't we factor out x squared out of this mess as well. So factor out an x squared. We're getting 12 from here, plus, now 4 plus 4 is 8x plus x squared. All right, times e to the x. All right, so we have our first and second derivatives. Let's find the critical numbers, or the critical points for this function. Well, this derivative is defined for every value of x, so there aren't any critical numbers that come from the derivative not existing. So let's take our derivative and just set it equal to 0. So 0 equals 4x cubed plus x to the fourth times e to the x. Now, since e to the x is never 0, it's safe to divide both sides by e to the x. We don't have to worry about the possibility that we're dividing by 0. So on the left we get 0, on the right we get 4x cubed plus x to the fourth. And to solve this, why don't we factor out x cubed? So 0 equals x cubed times 4 plus x. All right, so that means x cubed is 0, or the other possibility is that 4 plus x is 0. So either x is 0, or the other possibility is that x is minus 4. So we have two critical numbers, x equals 0 and x equals minus 4. Now let's plug both of these into the second derivative to see what the second derivative test has to say about these critical numbers. For x equals minus 4, we get, let's see, second derivative is, let's see, minus 4 squared is 16 times 12 plus, let's see, 8 times 4 is 32, so minus 32 plus 4 squared is 16 times e to the minus fourth. So this is 16, let's see, 12 plus 16 is 28, so minus 32 is minus 4 times e to the minus 4. And so this is going to be negative. Right? Remember, all we care about is whether it's negative or positive, because we just need to know the sign of the second derivative. And this is positive times negative, so it's going to be negative. And that means that x equals negative 4 is, let's see, when the second derivative is negative, you're at a local maximum. So this is a local maximum. All right. So what about x equals 0? Let's plug in into the second derivative. Let's plug in 0. Well, you can see that because of this x squared factor out in front, the second derivative at x equals 0 is just 0. And this is the case where the second derivative test doesn't tell us anything. So at this point, we can't tell if x equals 0 is a local min or a local max, or maybe it's not a local minimum or a local maximum. We just don't have enough information to tell at this point. This is one drawback of the second derivative test. So often the second derivative test is fast to use because you just have to plug in the critical numbers, but it is possible that the second derivative test is inconclusive because of this possibility that the second derivative might be 0. There are two ways to deal with this. Maybe the best way, or sort of the most in keeping with the theme, is the first derivative test didn't have this problem. The first derivative test didn't have this exception. The first derivative test always can tell a local min from a local max. So if the second derivative test is inconclusive, you can always fall back on the first derivative test. Of course, the first derivative test is a little more complicated. We need to build this sign chart. We have to put our critical numbers on our sign chart. So there's x equals 0 and x equals 4. Sorry, x equals minus 4, so we need a spot over here. And then to use the first derivative test, we have to check on the two intervals next to x equals 0, is the first derivative positive or negative? So we need some test points. How about at -1 and at +1? So we need to calculate the, I'm sorry, I'm writing f, this should be g. We need to calculate g prime of 1, and we need to calculate g prime of -1, so that we can know on the intervals next to x equals 0, is the first derivative positive or negative? Well, we have to go all the way back up to our formula for g prime, which is way up here. So this one right here. And you can see if we plug in +1, this is going to be all positive. So this one is, we didn't calculate exactly what it is, but it's definitely positive. So like this. And if we plug in -1, we're going to get -4 + 1 times a positive. So we're going to get negative times a positive, that's negative. So even without calculating exactly what this is, we can tell it's going to be negative. So the first derivative of g is negative from -4 to 0. And now this is enough information to use the first derivative test. So now the first derivative test says that x equals 0 is a local minimum, because our function is, the original function g is decreasing, and then we hit our critical number, and then it's increasing. So g itself looks like decreasing, and then horizontal tangent line, and then increasing, and that means that x equals 0 was a local minimum. Alright, so we can verify that this is right just by asking GeoGebra for a graph of this function. Let's just make sure that the graph that we get is compatible with what we found. So let's delete this one, and g of x is x to the 4th times e to the x. Alright, so here is our local minimum at x equals 0, and you can see why the second derivative test failed. The graph is so flat here that the second derivative is 0, and when the graph is so flat, concavity is essentially impossible to determine just from the second derivative at this single point. You know, our eyes are sort of naturally drawn to either side of x equals 0, so since we get sort of a holistic impression of the graph, we can tell easily by looking at the graph that it's concave up through this interval. But the second derivative test is really only looking at this single point at x equals 0, and it's so flat there that the second derivative test just can't tell what's going on. The other critical number we found was at -4, so if we zoom out a little bit, we should see something happening at -4, and sure enough, there's the local maximum at -4 that we predicted.